Okay, we'll come back to some of those that we were looking at again. But right now, let me explain something to you about a point of inflection. The first thing I want to explain to you is that a point of inflection must be a point on the graph where the inflection changes. A flexion can change across a vertical asymptote or across a gap in the graph, but that does not give you a point of inflection. So over here, the graph is actually concave upward, but over here it's concave downward. You can just barely see it. But the change in concavity doesn't change at a particular point. So there's no point of inflection. So we want to actually be able to find the points where the graph changes its inflection, which means changes concavity. So basically, the definition of an inflection point is this: if the graph of a continuous function has a tangent line at a point where its concavity changes, then the point is called a point of inflection. So basically, there has to be a tangent line. So here, you've got a tangent line here and you've got a tangent line here. So both of these can be points of inflection. So here, this graph changes from concave down to concave up at the point 2, 0. So that's a point 2, 0 is a point of inflection. Here it changes from concave up to concave down at the point 2, 0. So that's called a point of inflection. So properties of points of inflection. If you find a point, C, F of C, and you find that this point is a point of inflection, then either the second derivative is 0 or the second derivative is undefined at that point. Now, most of your points of inflection will be determined by finding where the second derivative is 0. So what you want to do is to find points where the inflection changes. You want to get the second derivative, then determine any values that make the second derivative 0 or undefined. Then we're going to test the second derivative near those values. So basically, I'm going to go back to some of these functions that we just did. We already did the legwork on some of these. Okay, so let's take a look at this example. Let's see if we can find points of inflection. Okay, so we're going to get the second derivative. All right, we did this earlier, but earlier we did this table so that we could check for concavity. Now we're going to actually identify points of inflection. So basically, your second derivative is 0 at -1 and 1. So we break the x-axis at -1 and 1. Okay, and then if you check to the left of -1, you'll see that the second derivative is positive, but just to the right of -1, the second derivative is negative. So since the sign of the second derivative changes at -1, that means at x equal -1, I'm going to get a point of inflection. But note, this says point of inflection, so that means you want the x and the y value. So I need to get the corresponding y value for -1. So the concavity changed when we crossed x equal -1. But what is that point? Well, go back up in here and plug -1 in for x. -1 squared is 1. Minus 6 times -1 squared is 1 minus 6, -5. So the point of inflection for x equal -1 is -1, -5. And then here at 1, to the left of 1, you get the second derivative is negative, and so it's concave down. And to the right of 1, the second derivative is positive, concave up. So it changes from concave down to concave up at x equal +1. So that's also a point of inflection because the concavity changes. So, and then to get the y value for that point, I had to go back up here and plug 1 in, and I got 1 minus 6 is -5. So those are the 2 points of inflection for that graph. So if you'll look, here's the graph of that one, and notice it's concave up till you get to this point, and then it turns back down till you get to this point, then it switches back to concave up. So these 2 points here are actually the points of inflection. Okay, so this next one here, y equal minus 4x cubed minus 8x squared plus 32. Again, I need to get the second derivative, and we know the second derivative is 0 at negative 2/3. And remember, when we tested it earlier, we found that to the left of negative 2/3, the graph was concave up, and to the right of negative 2/3, it was concave down. Well, I like to get the exact answers here and not use approximations, so I had to do some heavy arithmetic here to figure out the y value for negative 2/3. So you get negative 4 times negative 2/3 cubed minus 8 times negative 2/3 squared plus 32, and I came out to the fraction 800 over 27 for the y value. Now I'm going to show you a picture here, and it's going to show you this point of inflection, but it's going to give it to you in a decimal, so I can't help that. Alright, so here's a picture. Notice that the graph is bending upward till we get here, and that's your point of inflection, and then it begins to turn back downward. So there's your change in concavity. Alright, so for this one, y equal x cubed, you kind of know what that looks like. It's one of the basic graphs. So here's just a rough sketch of it. And this is the point 0, 0, because that's where the point of inflection is going to be. Alright, so the derivative was 6x. And remember earlier we tested that on each side of 0, because that's where the second derivative was 0, was at 0. And we found the graph was concave down to the left, concave up to the right. So when x equals 0, you're going to get a point of inflection, and the y value, just plug 0 back in here for x to get the y value, and here's your point of inflection, the point 0, 0. And you can see concave down to the left of 0, 0, then it goes concave up. Now this is just a parabola that bends upward, and remember we didn't have any change in concavity here. This was concave up all the way through, so there was no change, so there's no points of inflection. Okay, this one, remember we had a vertical asymptote at x equal 1, so we did have a change in concavity here. The concavity was concave down on the left, concave up on the right. But we cannot say there's any points of inflection, because actually you don't get a point at 1 for this graph. So I like to investigate what's happening around vertical asymptotes, but you're not going to get a point of inflection at a vertical asymptote. Let me show you the picture of this one. So here's the picture of the graph, and this is the vertical asymptote x equal 1. Notice to the left it's bending downward, so you have downward concavity, but to the right it's bending upward, so you have upward concavity. But there's no change in there's no point at which the concavity changed, so we don't have any points of inflection for this graph. Okay, so this one, I kind of went over this one quickly earlier, but let's go a little slower this time. The second derivative of this, and you know, I know it's not a lot of fun, but I got the first derivative to be 1 minus x squared over x squared plus 1 quantity squared, and then I used the quotient rule to get the second derivative. Well, if you look at this second derivative, there's actually, if you set this equal to 0 to get the zeros of that second derivative, well, it can only be 0 if x is 0 or if x squared minus 3 is 0. And x squared minus 3 can only be 0 if x squared equals 3 or if x is plus or minus the square root of 3. So that's where I got plus or minus square root of 3. So basically at minus square root of 3, at 0, and at square root of 3, though that gives us the intervals to check. So I need to check to the left of negative square root of 3, between negative square root of 3 and 0, between 0 and square root of 3, and square root of 3 to infinity. So I know square root of 3 is about 1.7, so negative 2 is less than negative 1.7. So negative 2 would be in this interval. And when I plug negative 2 into this second derivative, I actually got a negative. So that tells me the graph is concave down on that interval, on this interval. And then between negative square root of 3 and 0, I'm just going to use negative 1. And when I plug negative 1 into this, I got a positive value for the second derivative. And so I got concave up for the function. And then when I plug 1 in for this interval, I can use 1, and I got, when I plugged 1 in, I know it says 2, but I actually plugged 1 in. Okay, so when I plugged 1 in, I actually got a negative value, and then, so it's concave down in that interval. And then when I plugged, I needed a number greater than square root of 3, so I plugged 2 in, and the second derivative evaluated at 2 is positive, so we're concave up on this interval. So we actually change concavity here where x is minus square root of 3, and we change concavity when we go across where x is 0, and we also change concavity when we cross x equals square root of 3. Now, getting the y value for 0, that was easy. 0 over 0 squared plus 1 is 0. I'll let you do the hard part. If you plug minus square root of 3 in here, and then, you know, the bottom would be minus square root of 3 squared plus 1. It's not that difficult, but the bottom is going to get 4. So you're going to get minus square root of 3 over 4. And then for this one, when you plug plus square root of 3 into the function, you're going to get, for the y value, plus square root of 3 over 4. So these 3 points are your points of inflection. Now if you look at the graph for that one, the changes are kind of subtle. But you can see here there's a very subtle change of it's concave down, but it's very subtle here. And right here is minus square root of 3 and whatever the y value was. So that's where that point of inflection is. And then it changes to concave up. So it begins to bend upward. And then at 0, 0, it changes from concave up back to concave down. And then over here, this is where plus square root of 3 is. And so at plus square root of 3, it changed from concave down back to concave up. So, like I said, those changes are a bit subtle, but if you look closely, you can see the concavity changing. On some graphs, you can't really tell by using your eyes. You have to depend on the calculus. Okay, the next thing there's a couple of practice problems you can practice on with the answers given. I'm going to do one more video on this section, but in the next video I'm going to talk about how you can use the second derivative test to find extrema. So we're actually going to return to extrema using the second derivative in the next video.